Assalamu alaikum and good evening, everyone. Today we are going to start paper 2 AS level, May-June 2023 to 1. Okay. So let's start with the question number 1. Tellurium is an element in group 16. The most common isotopes of tellurium is tellurium-130. Its electronic configuration is krypton 4d10 5s2 5p4. Okay. They are asking for the nucleon number. So the value, this one is a nucleon number over here, 130. They are asking you the number of neutrons. So the number of neutron is 130 minus the atomic number. So we have to look into the periodic table, and is the atom. So if it's an atom, so the atomic number is equals to the number of electrons. So for these two, we are going to look at the periodic. So over here in the end, you get the periodic table. If you see tellurium, its atomic number is 52, right? So one 30 minus 52 will give me the number of neutrons, and 52 is the atomic number. So it means the number of electron is also going to be 52. So I'm going to write 52 over here. So if I subtract it, it's 8 and it becomes 12. 12 minus 5 means 7. So it is going to be 78. Is this clear to all of you? Okay. Now B part. Identify the subshell in an atom of tellurium that contains electrons with the lowest energy. So in any atom, when we have to see the subshell which has the lowest energy, so which subshell is this? Very good, Hassan. It's the S subshell of the first shell. So you have to write 1s. Now, C part. Construct an equation to represent the first ionization energy of tellurium. For first ionization energy, if you guys recall, the atom in the 1 mole of an atom in the gaseous state turning into 1 mole of a +1 charge gaseous ion and losing 1 mole of electrons. So that's how we will write the equation which represents the first ionization energy for any element. Okay, now D1, the radius of tellurium ion decreases after each successive ionization energy. Okay, yeah, obviously because the electron is lost, the number of protons stays the same. So the net nuclear charge or the effective nuclear charge increases. So the forces of attraction gets stronger, and as a result, the size decreases. State two factors that are responsible for the increase in the first 6 ionization energies of tellurium. So if we talk about the first 6, it means they are talking about when you are going to release the electrons from outermost shell, from the valence shell, because if you see in the valence shell, we have a 4 and 2, we have a 6 electrons. Okay, so as the electron is released, the nuclear charge increases, so the nuclear attraction. And what happens to the shielding effect? There is a little decrease in the shielding effect when we move after from 4 of these two over here, because now this from this shell is, if from this subshell the electron is being removed, so it has a relatively lesser shielding effect. So we will write nuclear forces of attraction increases as the net nuclear charge increased and The shielding effect decreases due to subshell from ionization energy 4 to ionization energy 5. It is because it's C5s2 and 5p4. So after these four electrons are removed, when we move to the fifth ionization energy, there will be lesser shielding, which also leads to increase in the nuclear charge and the decrease in the radius. Till here, is this clear to all of you? Okay. Now what they are saying in the part 2, sketch a graph in figure 1.1 to show the trend in the first 7 ionization energy of tellurium. Okay. For first 7, if you look at its electronic configuration, it is 4d10, 5s2, and 5p4. So for first 7 ionizations, first 4 electrons are going to remove from 5p4. Then 2 electrons are going to remove from 5s2. So 6 electrons are removed. No, there is a decrease in ionization energy, Benin. They have stated that the ionization energy is the radius of the tellurium is decreases due to the successive ionization. So successive ionization always increase because the net nuclear charge increase. And as a result, the nuclear forces of attraction increases, which leads, and as a result, they attract the less. Yeah, there is a decrease in shielding. It is because, see, the first 4 electrons are actually released from the 5p4, right? When the electrons are being removed from these, so what happens? So isn't it this subshell is also, causing the shielding effect? Right, Bunny? Okay, great. So when the electron is going to remove from here, so the other shells which are left over here are going to cause the shielding effect. So there is a one subshell lesser over here for this one, which causes the shielding effect. That's why the ionization energy decrease. That's why the shielding effect decreases. So the 2 electrons removed from 5s2. Now 6 electrons are removed. After these 6 electrons, now 1 electron is going to remove from 4d10. Is this clear? So if you see over here, from here, after the 4 electrons, there is a change in subshell, right? And after these 2 electrons, there is a change in shell. So remember that the shell change is always very bigger, right? So what happens to the first 4 electrons ionization energies? That they increase gradually like this. After 4th electron, the subshell is changed, right? So there is a little increase over here at 5th, and then there is a gradual increase to 6th. And then the 7th electron is actually getting released from the inner shell, the 4th shell, not from the 5th shell. So that's why there is going to, a very big increase in the ionization energy. So it would be like this: gradual increase, a little greater increase due to the subshell change, and then a very big increase because the shell gets changed. Okay. Now, E part. tellurium reacts with the fluorine at 150 degrees Celsius to form TeF6. The molecule of TeF6 is octahedral with a bond angle of 90 degrees. Explain why is octahedral with a bond angle of 90 degrees. So if you recall, whenever there is a octahedral, there are 6 bond pairs and no lone pair around central atom. And in this case, it's TeF6, so which is indicating us that tellurium is a central atom, right? Okay. Uh, yes, Umar, because if you look at the 7th electron, from where the 7th electron is going to release, the first 4 electrons are released from p subshell of the 5th shell. Then the next 2 electrons removed from the s subshell of the 5th shell. So the s subshell is little lower energy. So that's why the attraction would be little stronger. So there is a little increase. But the 7th electron is actually removed from the inner shell, that is 4d. So if it's for 5p is over here and 5s is over here, so 4d would be like over here. So see, there is a very big difference. That's why it for the electron to remove from the 4th shell, we need a very high amount of energy. So that's why there is a very big jump. Okay. And we know that if there are bond pairs only, so the bond pairs repel each other equally, and that's why we got only one angle, that is a 90 degree. Okay, so I'm going to write over here. There are 6 bond pairs and no lone pair around tellurium. And as we know, there are all the bonding pairs, so all the bond pairs repel each other equally. If there is a bond pair and a lone pair, so there are bond pairs, so the bond pairs repel with a lesser force as compared to the bond pair and a lone pair. And lone pair and lone pair are repelled with a greater force as compared to the lone pair and a bond pair. So, but here there are only bond pairs, so all the bond pairs repel each other equally. And that's why all the angles are same, which is 90 degree. Okay. Now F part. TeF6 reacts with water to form tellurium hydroxide and HF. The oxidation number of tellurium does not change during this reaction. Construct an equation for the reaction of TeF6 with water. Okay, they didn't tell you TeF6, they are using TeFX. So we are going to use the same way as they have told you TeFX, right? When it reacts with water, what we get? Tellurium hydroxide and HF. Okay. So if there are X moles of F over there, then when OH displaces them, so we are going to get X moles of OH over there. And HF has been formed. To balance the equation, we are going to put X as a coefficient over here. Is this clear to all of you? Oh, my screen is stuck here. It's slow. Is the complete equation is visible to all of you? No, it's not. Yeah. Now, F part 2. Name the type of a reaction that occurs when TeFX reacts with water. Yes, which reaction is it? Yes, very good. When it reacts in water and see in water, it's broken down, right? The T and F gets apart from each other. So that is called hydrolysis. And from here, we got to know one more thing. If it's the hydrolysis, then it means that it's a, a covalent molecule, a covalent compound. Is this clear? Now, question number 2. A neutralization reaction occurs between aqueous sodium hydroxide and a sulfuric acid. Equation 1. See, sodium hydroxide is reacting with sulfuric acid to form salt and water. Okay. Define the enthalpy change of a neutralization. So see, you guys need to remember the definition. So we can write that it is the enthalpy change when 1 mole of water is formed from acid and an alkali. Today the net is not working properly. Just give me a minute, guys. Okay. Now, B part. An experiment is carried out to calculate the enthalpy change of neutralization for the reaction between sodium hydroxide and a sulfuric acid. Okay. 100 centimeter cube of 1 mole per dm cube sodium hydroxide. Okay. So let's do a little homework over here. Sodium hydroxide volume is 100 centimeter cube and its concentration is 1.00 mole per dm cube. Is added to 75 centimeter cube of 1 mole per dm cube sulfuric acid. So the sulfuric acid volume that we used in this experiment is 75 centimeter cube and the concentration is 1 mole per dm cube. In a polystyrene cup and stirred, results from the experiment are shown in table 2.1. Okay. Use the equation 1 to calculate the amount in moles of sulfuric acid that is neutralized in the experiment. So see, they didn't ask you for the total moles of sulfuric acid. They ask you the number of moles of sulfuric acid that are neutralized. It means that have took part in the reaction or they have used up. So if you find the moles of sodium hydroxide, so we know the formula. We have to multiply the concentration with the volume, but volume must be in decimeter cube. So we have to divide it with 1,000. So I think 0.1 into 1, you will get the number of moles of sodium hydroxide is 0.1 mole. Can anyone confirm me, please? And for sulfuric acid, it's 1.00 times 75 over 1,000. So I think it's 0.075 moles. Can anyone confirm it, please? Okay. Now, if you look at the equation, there are 2 moles of sodium hydroxide which are reacting with 1 mole of new sulfuric acid. So you have to take this ratio to figure out how much moles of sulfuric acid is neutralized or used up. So sodium hydroxide is to sulfuric acid. And from the balanced equation, the ratio is 2:1 because there are 2 moles of sodium hydroxide and 1 mole of sulfuric acid, right? So the moles of sodium hydroxide used is 0.1 And for that 0.1 moles of sodium hydroxide, we use X moles of sulfuric acid. And if you calculate the X moles of sulfuric acid, it is going to be 0.1 times 1 divided by 2, and you are going to get 0.05. So the number of moles of new sulfuric acid that are neutralized is 0.05. So remember, these are the moles which are neutralized or which have been reacted out of these number of moles. So it means that sulfuric acid over here is in excess and sodium hydroxide over here is a limiting reactant. Is this understandable to all of you? No, my screen again is stuck. So the total moles of sulfuric acid available are 0.075, and out of that 0.075, 0.05 moles are neutralized, which means that some of the sulfuric acid left behind. So it's a excess one, and sodium hydroxide is the one which is limiting reactant. Okay. Now, calculate enthalpy change of neutralization using the results in table 2.1. Include units in your answer. Okay. Assume that the specific heat capacity of final solution is 4.18 joules per gram per Kelvin. So it's a C. 1 centimeter cube of final solution has a mass of 1 gram. So see, we got the mass, that mass is equals to volume. Whatever the volume that have been used, the same, will be the mass of. Okay. There is no heat loss to the surroundings. Okay. Now, full dissociation of sulfuric acid occurs. Okay. The experiment takes place at a constant pressure. Okay. So if you see the total volume, we have used 100 centimeter cube and 75 centimeter cube, right? So the total volume is 100 plus 75. So the total mass is going to be 100 plus 75, which means 175 grams. Okay. So if you recall the enthalpy change of neutralization or enthalpy change formula, so the enthalpy change formula was minus mc delta T over n times 1000, right? So minus 175 times the specific heat capacity, which is given over here, 4.18, times change in temperature. So change in temperature was initial minus final. Sorry, final minus initial. So 278 minus 20. Sorry, 227.8 minus 27.8 minus 20. So we got the three values divided by number of moles. Okay. So sodium hydroxide is a limiting reactant as we have decided. So we are going to use its moles that are 0.1. So 0.1 times 1000. And why we doing it times 1000 in the numerator, in the denominator? It is because from these, when we get the energy that is in joule, so we have to convert it in a kilojoules, and dividing by mole, it will turn into kilojoules per mole. So can anyone calculate and tell me that, please? It is the enthalpy change formula, not for neutralization, okay? Because see, the total volume that we have used is 100 centimeter cube of sodium hydroxide and 75 centimeter cube of sulfuric acid. So it means the total volume used was 175 centimeter cube, right? And they have mentioned over here 1 centimeter cube of the final solution has a mass of 1 gram. So the total volume that we used was 175 centimeter cube. So it means that the total mass would be 175 gram. Is this clear to all of you? Okay. Yes, Kubra has calculated. Okay. And we have to write in a 3 significant figure. So if we will write it in the 3 significant figure, it is going to be minus 57.1. And the unit would be kilojoule per mole. Yes. So when we write it in a 3 significant figures, it's the actual answer is minus 57.057. So when we write it in 3 significant figures, it will become minus 57.1. Okay. Now, C part 1. Complete the equation for the reaction that occurs when a solution of barium hydroxide is added to aqueous sulfuric acid, include state symbol. So, okay. So what will happen? An acid and a base. So we are going to get salt and water. So water over here for a salt, if you work with the charges of ion, so it is going to be Ba2 positive and SO4 2 negative. So we just need to add them. Okay, now the state symbols. Water is a liquid, but barium sulfate is a solid. So you are going to put a S over here. It's again not working. Let me reshare the screen, okay? It's again stuck. Yeah. And the equation is balanced, right? Screen is not working properly. Okay. Now suggest why the enthalpy change of neutralization cannot be determined using the addition of a sulfuric acid to aqueous sodium hydroxide, barium hydroxide. Am I audible to you guys? There is a little lag in the screen due to the, I think, internet issues. So it is because if you see, whenever the neutralization occurs, neutralization is for the salts which salts are aqueous only, because these two are aqueous and the aqueous salt is formed. There is no precipitation, there is no solid particles form over there. Okay, so they are asking that why the enthalpy change of neutralization cannot be determined. It is because as the in the above equation, if you see the salt formed is a solid, there are the precipitates of the salt. So obviously, as the precipitates are formed instead of aqueous, so those precipitates, formation of precipitates also involves some energy change. So we get the total energy change, and we are not just able to get just the enthalpy change of neutralization only. So that's why we are not able to calculate the enthalpy change of neutralization over here. So we can write that as the precipitate of barium sulfate also involve some energy change as solid is formed. Is this clear to all of you? Now, we have a question number 3. Chlorine is a very reactive element. Chlorine reacts with a silicon to form silicon 4 chloride. Describe the appearance of silicon 4 chloride at room temperature and pressure. State its structure and bonding. Okay, yeah. So if you, what will be the formula of silicon 4 chloride? Yes, very good, Hassan. It's a liquid because if you recall the formula, it is going to be SiCl4 and chlorine forms only one bond. So it's a simple molecule. So whenever it's a simple molecule, so usually the simple molecules are usually either gases and a liquid. So it's a liquid. It is a liquid and structure. So it's simple molecular and covalent bonding. Okay. Now, samples of magnesium chloride and phosphorus 5 chlorides are added to separate beakers of a cold water. Complete the table 3.1. Ignore temperature changes when considering the observation for these reactions. So we are not going to mention that the container becomes warmer or the container becomes cold or cooler because they have already mentioned. Okay, so magnesium chloride, it's an ionic compound, right? And it's from group 2. So obviously it's colorless or a white. So we are going to write white solid. Okay. Phosphorus 5 chloride. Okay, its formula would be MgCl2 and its formula is PCl5. So it's a simple molecule, but it's a white solid. One similarity in observation on cold water. When both dissolves, that's what you have to remember. Because the covalent compounds, the simple molecular ones, some are solids, some are gases. Okay, very few are solids, simple molecules, the covalent ones. Most of them are liquids and most of them are gases. So you have to remember this thing. Okay. That which ionic covalent compounds are solids, which are liquids, and which are gases. That's what you have to remember. That everyone has to be remembered. Okay. One similarity in observation on addition to cold water, as both are white solids, so when they gets dissolved, what solution we get? We always get a clear or a colorless solution, right? So over here, the common observation would be colorless solution is formed. Now, one difference in observation on addition to cold water. Okay, if you recall the equations, when magnesium chloride reacts, it will, if you guys recall the complete equation, it will react with the 6 moles of water forming MgOH H2O5 and HCl. But if you recall this equation, so here the HCl is aqueous because very small amount of HCl has been made. But if you recall the reaction of PCl5 with water, we are going to get a phosphoric acid and 5 moles of HCl. And here, due to the 5 moles, it would formed as a gas. So we are getting the steamy fumes. Okay, it will appear in a why, Hassan, because the net is not working. Net is slow today. Okay, so here we get a steamy fumes. So see, due to more amount of HCl, you will get a steamy fumes with a PCl5, but no steamy fumes because HCl is formed stays aqueous, so no steamy fumes with magnesium chloride. So I'm going to write over here, no steamy fumes, and here we will get our steamy fumes. pH of the final solution. So if you recall the pH of the magnesium chloride solution, it's around 6.5. And here, as it's a strong acid, so you can write either 1 or 2. Okay. Now, C1, state the reagent and conditions required for the formation of sodium chlorate 5. It means it's chlorine having a +5 oxidation state. And for that, if you recall the formula, the compound is NaClO3. So if you guys recall to make or to prepare NaClO3, we need hot concentrated sodium hydroxide. If we use cold dilute aqueous sodium hydroxide, then NaClO is formed. So hot concentrated aqueous sodium hydroxide. Now, explain why the reaction in C1 is described as a disproportionation reaction. Your answer should refer to relevant species and their oxidations. Okay, so if you recall, our disproportionation reaction is the one in which one species oxidized and reduced both. So I will write over here that the oxidation number of chlorine increases and decreases. And here I'm going to mention chlorine when it's increases. See, it's a Cl2, right? So from Cl2, where its oxidation number is 0, it turns to form NaClO3, where the chlorine becomes +5. Beside this, NaCl is formed where the oxidation number of chlorine is -1. So over here increases, it goes from 0 to +5. And when we are saying it decreases, so it goes 0 to -1. Is this clear to all of you? Yes, is this clear? Okay. Now, D part 1. Chlorine reacts with a methane in a series of reactions to produce chloroalkane. So see, this parts come from organic. State the conditions required for the chlorine to react with methane. So if you guys recall the condition to react with methane, it's a UV light, right? Yes, very good, Benny. So we need a UV light or UV rays or sunlight. Okay. Now, see, this part is relatively easy. Part 2. Okay. So we are keeping today's class till here. And tomorrow we are going to finish this whole paper and we will continue from here onwards. Okay. So see you everyone tomorrow. Take care. Goodbye and Allah Hafiz.